Hello, everybody. So today I'm going to talk about control barrier functions for non-holonomic systems under RISC signal temporal logic specifications. My name is Lars Lindemann and I'm a postdoc at Penn. And this is joint work together with my postdoc advisor, Professor George Papas from Penn, and my PhD supervisor, Professor Dimos Dimarogunas from KTH. What we would like to have in the future are intelligent systems that are capable of achieving complex missions. Temporal logics have been used to formulate exactly such complex mission specifications. We focus here on quantitative temporal logics that, for instance, allow to formulate that a team of drones, shown over here, should repeatedly surveil certain areas with a certain precision and within certain time intervals, and to recharge batteries whenever needed. Most of the current approaches that exist to control such systems under temporal logic specifications consider purely deterministic systems in known environments. However, realistic settings impose additional challenges such as imperfect visions, as depicted in these two figures, and other stochasticities such as wind disturbance, shown over here, affecting the control system. To account for this, we necessarily need to use stochastic and robust control techniques. The contributions of this paper are twofold. First, we define RISC signal temporal logic, and second, we show how to convert the RISC signal temporal logic control problem into a deterministic one. Okay, so let us now discuss a bit the challenges that one may run into when one combines temporal logics with stochastic elements, such as random variables. Therefore, assume here the deterministic vector x and the random vector capital X over here that may be normally distributed, but may also have any other distribution. A normal distribution is shown over here. Again, such a distribution consists of a mean and a variance. The important observation is now that a function h that depends on x and capital X becomes yet another random variable. Typically, signal temporal logic predicates, or for short RiSTL predicates, are defined like this. So the predicate mu becomes true whenever the predicate function h evaluated on x and capital X is greater or equal than 0. Now, however, since this h of x capital X is a random variable, these RiSTL predicates are not well defined anymore. A possible remedy is to instead define chance predicates that are true whenever the probability that h is greater than 0 is greater than some delta. However, such chance predicates fail in particular to address the risk of not satisfying this predicate here. Risk can informally be introduced as considering the loss for realizations where h is smaller than 0. So in this figure, we have the random variable minus h on the x-axis and the probability density function on the y-axis. Chance predicates here in particular address this region where h is greater than 0, whereas risk measures such as the mean, the conditional value at risk, and the value at risk over here consider the tail of the bad events of the realizations where h is smaller than 0. In this paper, we define risk predicates that are true whenever a risk metric r that is put on top of minus h is smaller than some gamma. This risk metric r can be the expected value, the value at risk, and the conditional value at risk, but also any other risk metric from the literature. Let's now focus on the value at risk and the conditional value at risk. The value at risk at level beta is defined such that the probability of a loss greater than the value at risk at level beta is at most 1 minus beta, so this line over here. The conditional value at risk at level beta, on the other hand, is more risk averse and a coherent risk metric. In particular, it is the expected value given the values of minus h that are greater than the value at risk. So basically an expected value over this region. Okay, so based on these chance and risk predicates, we can now define risk signal temporal logic. Therefore, we take the chance and risk predicates here as the atomic elements on which we put Boolean logics. Here, negations, conjunctions, and also disjunctions. As in signal temporal logic, we additionally put so-called temporal operators on top. Here, the until operator that says that phi prime should be true until phi prime prime becomes true at some time instant within the time interval AB. I'm not going to provide the semantics here, but I want to provide an example that gives some more intuition. Assume therefore a trajectory, here x1 or x2 shown in the figure, and assume also capital X here that describes the stochastic environment consisting of two regions to be avoided, O1 and O2, and one region, R1, to be reached over here. The risk signal temporalogic task here then says that always between 0 and 6 seconds, these two risk predicates here should be true. These risk predicates put an upper bound on the risk of the deterministic trajectory entering the regions O1 and O2 over here. At the same time, the task says that eventually within 0 and 6 seconds, this risk predicate here, describing the risk of not reaching the region R1, should be true. What I'd next like to briefly show is how we can define quantitative semantics associated with the risk signal temporalogic task. Therefore, assume that X now is a deterministic signal, while capital X here is a random signal. What we do in the paper is we define quantitative semantics rho phi that depend on these two signals and on time t, and that indicate how well these two signals satisfy the risk signal temporalogic task phi. In particular, we show that whenever this metric rho phi here is positive, it implies that these two signals satisfy the task phi at time t equal to 0. I'm not going to go into details here, but the definition follows recursively. And for chance predicates, we define the quantitative semantics as the probability of h being greater than 0. And we subtract this chance bound delta. For risk predicate, on the other hand, we take the risk bound gamma and we subtract the risk metric that is put on negative h. And the other definitions here, they follow standard RiSTL quantitative semantics. Let us consider the previous example, but now evaluated on two different environments, capital X, that are drawn from multivariable normal distributions. In the left figure and indicated by the dotted circles, we can see that the uncertainty by which the regions O1 and O2 are described is smaller than in the right figure over here. The question that we would like to answer is, does trajectory x1 in blue or trajectory x2 in red satisfy the signal temporalogic task better? This can be seen here in the left figure with small uncertainty that both quantitative semantics based on risk predicates and based on chance predicates say that the signal x2 in red going through the middle is more favorable. On the right-hand side, where the uncertainty is bigger, the quantitative semantics here based on chance predicates still indicate that the trajectory through the middle is more favorable. However, the quantitative semantics based on risk predicates are more risk aware and now say that the trajectory x1 over here is favorable, hence going around the obstacles is the choice to go. What I'd now like to show is the idea that we present in the paper in order to translate a risk signal temporalogic task into a signal temporalogic task. We first define the chance and risk constraint sets as the set of X that satisfy either the chance or the corresponding risk constraint. We also define a deterministic set X that depends on a constant C based on a function H that is now evaluated instead of capital X by its mean value over here. The idea is that this deterministic set here, or that is obtained on this deterministic function, under approximates the chance and risk constraint sets as shown in this figure. This under approximation that has been shown on the previous slide now triggers the question on how can we actually select a C such that such an under approximation is achieved. So what we then show in the figure that checking this set inclusion based on a certain C can be solved by a convex program. So basically we obtain an X star that is obtained by the solution to this convex program. And then we plug in this X in the corresponding chance constraint or in the corresponding risk constraint. And if this chance or risk constraint holds, then we definitely know that the desired under approximation is established by the certain C. The consequence of this is that we translate a risk signal temporalogic task into a signal temporalogic task so that we can use deterministic RiSTL control methods for our purpose. In particular, we can define the following RiSTL predicate that now depends on this deterministic function. And what we then do in the paper is that we replace each chance and risk predicate in the risk signal temporalogic formula phi by this deterministic STL predicate to obtain the STL formula var phi over here. The theorem that we then prove is that if these C's have been selected properly, where properly is defined in the paper, then every X that satisfies the STL formula also satisfies the risk signal temporal formula. Let us now look at the control problem that we here consider. In particular, we look at non-holonomic systems described by unicycle dynamics, where F over here is a known internal dynamics term, G over here describes the unicycle dynamics, and C over here are unmodeled dynamics that are unknown, where only an upper bound is known. The problem that we then consider is that we would like to derive a feedback control law such that the quantitative semantics of the risk signal temporal task are lower bounded by some R that is greater than 0 and that is maximized. Let us now briefly talk about the control design that is based on a near identity diffeomorphism that switches the position coordinates x into the transformed position coordinates p. What we then do is we encode the STL task var phi into the barrier function b based on our previous work that I'm referring to here. And we do so for a suitably selected L, where L is described in the paper. We then achieve that the quantitative semantics of the risk signal temporal task phi are lower bounded by 0 by this control law that is based on terms b1 and b0. b1 in particular depends on the gradient of b with respect to p and on the system dynamics gp. b0, on the other hand, depends on gradient information of b with respect to p and with respect to t, and also contains a term here of the extended class k function alpha and b, as well as the upper bound c on the unknown dynamics. In the paper, we also show how we can lower bound the quantitative semantics by some R, where R is maximized. Let us now look at the simulation example, where the task is to avoid the region O1 and O2 over here with some given risk, and at the same time to eventually reach this region with some probability, and after that to eventually this region here with some probability. Importantly, what we can note, due to the risk constraints, the system is not allowed to enter this region over here, as well as this region over here. So the system, initially starting from here, is only allowed to go below the obstacle O2, enter the region over here, and then go back to enter the region over here. The simulation results that we obtain then exactly shows this. So the system is going in this direction, below the obstacle, enters the region R1, and then eventually enters the region R2. With that, I'd like to thank you all for your attention. I'm happy to answer any questions.